They've got a global voice over IP native network. The cable companies have all said they're going to, so the phone companies will all have to as well. All carriers will be deploying this picture. Now, what does it get us in terms of benefits? Well, we have a couple of different cases. Let's think of residential service in North America. So we're not talking about developing countries, we're talking about the United States and Canada. What does it get a residential customer? Well, it gets them better web surfing is what it gets them. Of course, it does telephony, but we've already got that flat rate long distance using traditional telephony right now. So what's the big deal in getting voice over IP long distance for slightly cheaper? I mean, it's unclear that that's a huge benefit. But to be able to support this, the carriers are going to have to beef up their access networks in all the major cities. And since we're using those access networks not just for voice but for data as well, the benefit that residential users in North America are going to see of deployment of voice over IP is faster web surfing. For people in developing countries, they're going to see cheaper long distance, possibly even better telephone service, because there will be a whole raft of competitors springing up to provide local access as well as long distance. So you think of places like Bangladesh, they're going to have toll quality speech anywhere that there's an internet connection, whereas maybe before this there was one telephone per village. For business and government, the big advantages here are better IP networks for communicating data, not just having a gigabit Ethernet over fiber access, but actually having the carrier put in enough horsepower so that you could do a gigabit per second from New York to Washington, D.C. So just like home users, there's going to be a huge advantage in terms of improving the underlying IP network that will make our data communications work a lot better, web surfing. And for a business or government organization, there is going to be a savings in voice communications costs. And where this savings in absolute terms might not be a huge deal for a resident, if we're talking about an organization that has a phone bill measured in the millions of dollars a year, then saving a couple of dollars per line per year is going to make a difference. And also, if we can get service where we bypass the local exchange carrier and stop paying them their switched access charge for long distance, that's going to be a cost savings as well. It's unclear how long that might last for. At present, it's not regulated, but you can be sure that that's going to change in the future. Now we're going to discuss how we might actually implement prioritization of voice over data on a wide area network. And this is to implement quality of service guarantees. In a perfect world, we wouldn't need to do this because we would have infinite capacity between point A and point B. So regardless of how many people were going over it, there are no slowdowns or congestion or lost packets or anything like that. But of course, in the real world, we don't have unlimited capacity. And in fact, the capacity is overbooked by the carriers because statistically speaking, people are not transmitting information most of the time. Statistically speaking, they're doing nothing. So the internal circuits in a network are overbooked. The question arises, if everybody tries to transmit at the same time, what sort of quality are you going to get? And how do we manage that? This slide shows the phone company's solution to this problem, ATM, asynchronous transfer mode. The basic ideas of ATM essentially are three. One of them is that we take everything and chop it up into little tiny chunks called cells to confuse people, and this holds 48 bytes of payload and there's a 5-byte header. That's one idea. Another idea is that everything is connected using virtual circuits. And a virtual circuit is a path. It's a route. It's a possibility. It's a path between every two pieces of network equipment all the way to make a chain to get from one end to another. And that path is stored as entries in databases in all the pieces of the network equipment. And the path is identified with a virtual circuit ID. The idea is if you want to communicate from A to F, we would establish one of these paths, these routes, these virtual circuits, and then normally you would do nothing. And then if you wanted to actually communicate information, we would send packets or frames or cells into the network. They would follow along that predetermined path and then be delivered out the far end sometime later. ATM uses this idea of virtual circuits. Now the third idea here, and the one that we're really interested in this discussion, is that with each virtual circuit in ATM, we can assign a service class. And a service class is like a contract with the network. And what it does is it specifies on a particular virtual circuit what kind of performance we're going to guarantee. And there are a whole list of these different service classes. The best quality of service you can get on an ATM network is a permanent virtual circuit with continuous bit rate assigned as the service class. And what continuous bit rate means is that if squeaking noises weren't coming out of your face, or you weren't actually sending any data type information, then no capacity would be used on the fiber backbone connecting those two ATM switches together. But if squeaking noises did start coming out of your face, then you would instantly have the highest priority, and the switches would kick people with lower classes of service off to make sure that your stuff went across just as if it were a dedicated T1, for example. The next lower class of service is variable bit rate, but where the timing is important. And this is for video and audio and speech. Let's think of video. It doesn't take very many bits per second to code a blue screen, but it takes a lot of bits per second to code a chessboard moving around like this. So the number of bits per second that we're using varies depending on what the complexity and the changes in the image are, or in the speech, same story. But the timing is very important. Every one of those video pictures has to arrive on time, and the same thing for speech as we were talking about with jitter. So this would essentially have a jitter specification associated with it if you want to tie it back to voice over IP terms. But you're not allowed to just transmit continuously at your line speed. You have agreed that the average number of bits per second you're going to transmit is this, and you might go over it, but you can only go over it this high, and your burst overage only lasts for a certain period of time. And the idea with this service class is that as long as you respect what you signed up for, they guarantee they're going to deliver it. If you transmit more than what you signed up for, that's not guaranteed. The next lower service class is variable bit rate, but where the timing is not guaranteed. What's this? Well, that's frame relay and the internet, where the number of bits per second you're transmitting is varied, and there are no guarantees in the network as to the jitter and the delays getting from end to end. So the way that a carrier actually would provide frame relay is they would take their fiber network, they'd run SONET over there for management, they'd stick ATM switches at each end and connect them together with SONET channels, and then they'd front end that with frame relay boxes and tell the users, okay, connect your frame relay on here and our frame relay network will deliver it over there. Unbeknownst to the user, what happens is that frame relay network equipment takes the frame relay frame and chops it into ATM cells and transmits them with all of the other ATM stuff on a virtual circuit with class of service variable bit rate non-real time to the frame relay box at the other end that then reconstructs the frame relay frames to deliver them over, say, a T1 to the user at the far end. This idea is called ATM transport.